Hi everybody, this is Francesco D'Amore, and in this video I'll talk about the paper No Distributed Quantum Advantage for Approximate Graph Coloring. The other authors of this paper are Xavier Roy, Rishikesh Gajjala, Fabian Kuhn, François Legale, Enric Lievonen, Augusto Modanese, Marc-Olivier Renou, Gustav Schmidt and Jukka Suomela. Let's define the problem of interest, approximate graph coloring. We're given two input parameters, chi and c, with c being no less than chi and chi being no less than 2. Those are integers. And a chi-chromatic graph G, and we are required to produce a C coloring of G. So for example, for C equals 4 and chi equals 2, and the input graph being a grid, we can just out a 4 coloring of the grid, and similarly for when you require 4 coloring of odd cycles. We are interested in solving this problem in the local model of computation. It's a fundamental model of distributed computing introduced by Lineal in 1987. Here the input graph is the distributed system, so nodes are machines, and they have unique identifiers in the set from 1 to n to the power of c, where n is the number of nodes. Time is asynchronous, and all nodes run the same algorithm. In this more specifically, at each round, every node performs local computation, updates its state variable, and then sends messages to all neighbors and also receives messages from all neighbors. In the local model, there are no constraints on the computational power and no bandwidth limitations. And within these constraints, the distributed system can solve a problem on basically itself, like coloring. The complexity measure of a problem in this model is just the minimum number of communication rounds required to solve a problem, and I want to stress the fact that there's a link with locality. Basically, let's look at the distributed system from the perspective of the red node, and let's imagine that three communication rounds have occurred in this system. Then all the informations that this node knows come from distance at most 3 from it, because we have performed 3 rounds of communications. And so it is equivalent to perform 3 rounds of communication, and to look instead of at distance 3, and at all nodes at distance 3, gather all the information available and also the topology of the graph. This is completely equivalent, and so we can also talk about the complexity in terms of minimum locality required to solve a problem. Of course, an algorithm with locality diameter of the graph plus 1 solves every problem, because a node can just gather all the graph locally and then solve the problem and output the solution. Now let's look at the complexity of the problem of interest. So if chi equals 2 equals c, basically the problem, we cannot do anything better than the trivial algorithm of gathering everything and outputting the solution. And the lower bound is also trivial, because basically there are synchronization problems between faraway nodes. A bit more interesting is the case of 3 coloring bipartite graphs, where nothing better than the trivial algorithm was known, but there was a lower bound of square root of n shown by Brand et al. In 2017 that came from the case of grids of size square root of n times square root of n. As for the case of 4 coloring bipartite graphs, again nothing better than the trivial algorithm is known for the upper bound, while the lower bound is log n and comes from the fact that there exists high girth, high chromatic graphs. More in general, when chi equals c, the case, so the complexity is the same as the case 2 and 2, while for general parameters chi and c, what was known is the same as the case of chi 2 c4. Log n comes from the same example of high girth, high chromatic graphs. So what we do is to basically close this table. So for the case of 3 coloring bipartite graphs, we show that the lower bound was actually tight, and there is an almost matching upper bound of square root of n, while for the case of 4 coloring bipartite graphs, the correct bound is the cubic root of n. And more in general, if we define this parameter alpha to be the integer part of c minus 1 over chi minus 1, this is some kind of approximation ratio, then The complexity of the problem is roughly n to the power of 1 over alpha up to polylogs. So basically we solved the problem, but the surprise is that this result holds for a wide range of distributed problems. It holds for the deterministic local model, it holds for the randomized local model where nodes have access to private randomness. It holds for randomized local model with shared randomness. It holds for the quantum local model and the quantum local model with shared quantum state. It holds for finitely dependent processes and for the non-signaling local model. Here an arrow means that an arrow from model X to model Y means that an algorithm in model X can be simulated in model Y with the same locality, implying that model Y is stronger than model X. And so we show a lower bound in the strongest model and the almost matching upper bound in the deterministic local model, making all this model collapse for this specific problem of C-coloring chi-chromatic graphs. So now let's define the non-signaling local model. It was introduced by Gavois et al. In 2009 and then analyzed again by Arfawi and Fregnault in 2014. Basically, it's stronger than any physical synchronous distributed model and it has a purely probabilistic definition. So no background in quantum information theory is necessary to understand the model. And the only constraint in this model is the non-signaling principle. Informally, it says that no signal can be sent from the future to the past. And in practice and formally, we say that the non-signaling local model produces non-signaling outcomes. An outcome is just a function assigned to an input graph with some input parameter x, a distribution over solutions, in our case C-colorings, represented as a family of pairs where yi is just a coloring and pi is the probability that the coloring occurs. Of course, the sum of pi's must be 1. And an outcome can be non-signaling beyond distance t if the following property holds. So we fix a vertex set V, and for every subset of the vertex set and for every pair of input graphs on the vertex set such that the radius t views around the subset S are the same, also with respect to the inputs, then the coloring distributions of the outcome restricted to S are identical. This is the non-signaling property in mathematical terms. And intuitively, let's see what happens with algorithms, since algorithms also satisfy this property. Let's fix a distributed system with n nodes, as in the picture, and also a subset of those nodes. And let's run an algorithm A for t rounds, in the picture t equals 2, and consider the t neighborhood of these red nodes, in the picture the green region. Now if we just modify the graph outside the green region and we run again the algorithm, we have that the output distribution over the red nodes must be the same no matter the structure outside, because what they see in the green region didn't change. This is the non-signaling property, and it is satisfied by all physical algorithms. And basically the non-signaling local model produces these non-signaling outcomes, abstracting this idea. So algorithms are not required. You can just design from scratch the output distribution as long as the non-signaling property is satisfied. Now let's give an example for the lower bound, in the case of 3 coloring 2 chromatic graphs. We said that the complexity was roughly square root of n, and we'll show this first in the deterministic local model and afterwards for the stronger counterparts. The idea is to find a graph H that is locally 2 colorable, but the chromatic number is at least 4, so that the problem on the whole graph is not solvable. And this graph exists and is very similar to a grid where borders vertical borders are connected in a torus, like in a torus, while the horizontal borders are connected in a more specific way. Basically, this second node on the bottom is connected to the last node on the top, the third node on the bottom is connected to the second to last on the top, and so on and so forth. So it's like the reverse order of what one would expect in a torus. This graph is a quadrangulation of the Klein bottle, and in this specific drawing it's a node quadrangulation. Locally, it is like a grid, but globally, the chromatic number is 4. And the idea is that we proceed by contradiction. Assume that there exists an algorithm that is giving 3 coloring of bipartite graphs that works with some small locality, a locality that is small enough so that in this graph a node cannot understand that the chromatic number is different from 2. So every node with this locality will just see a grid, basically. Now we apply this algorithm to H, which is always possible because of what we just said. But of course there must be a failure, because H has chromatic number 4. And a failure means here that 2 adjacent nodes will have the same color. Now let's fix the T views around these 2 nodes, which will still be a grid because this T is small enough. And then we construct, by cloning this region, a 2-colorable graph G, which is then an admissible instance that has this isomorphic region. Of course, these 2 nodes will produce the same failure because their output depends only on what they see inside this region. And this is a contradiction, and such an algorithm with this small locality cannot exist. And the idea behind this argument is the cloning principle, which says that the same effect holds if the local views are indistinguishable. And this technique is called a graph existential indistinguishability argument. It's a lower bound technique that works also in randomized local, but of course it's a bit different because here we can locate specifically the failure, and the failure happens deterministically. It is not the case in randomized local, but we can overcome this issue. So we fix the same bad graph. Now we have to basically subdivide the graph in many regions, possibly overlapping, such that the T neighborhood of any of these regions is 2 colorable. And here we can achieve this with 4 different regions. T will be a bit smaller, roughly square root of n over 4. And now if we imagine by contradiction that there is an algorithm that is able to 3-color bipartite graphs within this locality, applying this algorithm here again leads to a failure with probability 1, but the failure can be anywhere. But for sure we know that in at least one of these 4 regions there is probability 1 over 4 to get to have a failure. So we specifically focus on that region. And then we have to require that we can take many copies of this region together with the T view around it and glue them together to form a 2-colorable graph, which is an admissible instance. And in this case it is possible because basically we are taking 2 colorable graphs and just adding some edges here and there will keep everything 2 colorable. Now the failure in each of these regions happen independently with probability 1 over 4. And so by independence and the union bound we have that the overall failure probability in this new graph is high enough. Here k equals 4, and so we then can take n as a large enough constant, and we can have a probability of failure that is bigger than 99%. Of course we are paying a price in the locality because here we are adding many nodes. And so the argument of the locality will be divided by this big N, which is the number of times we are cloning the bad region. But if you find the right combination between K and N, nothing changes. In this case, big N is a constant. So asymptotically, everything remains the same. What about non-signaling local? In non-signaling local, we have some problems. Here I have reported a definition of the non-signaling local model because I want to stress the fact that the non-signaling property holds only for pairs of inputs that have the same number of nodes. So you cannot consider different inputs that have different number of nodes. This is due to the no cloning principle, which means that there are no guarantees if basically we change the number of nodes. So, and also in the non-signaling local model there might be dependencies among faraway parts of the graphs because the non-signaling local model generalizes also the idea of shared resources like shared randomness or shared entanglement or whatever. So this idea of taking a cheating graph where locally the problem is solvable, but globally it is impossible to solve the problem, identifying a bad region and cloning the bad region many times to boost the failure probability in some admissible input is not possible. We cannot do that because we are changing the number of nodes, basically. So what we can do is we can actually address no cloning by considering many copies of the cheating graph. Now we will consider many copies of the cheating graph, big N copies, so that once we identify some bad region that will be that will consist in let's say parts of every of these graphs, of each of these graphs, we don't have to add the new nodes or remove nodes, but we will just use the remaining nodes to basically form an admissible instance just by rearranging edges. And now we cannot just identify a bad region in each of these graphs and glue them together, because there might be dependencies, right? So we consider instead joint probabilities, so sequences of let's say regions of these graphs, and we can prove and it is non-trivial that there is a sequence of regions of these graphs that has a high failure probability. This failure probability is exactly as in randomized local, but it's in spirit a different bad event, because we are not finding the region that in each graph has the highest failure probability, because in different graphs there might be dependencies. Instead, we consider the joint probability of all of them together. Then we copy paste this sequence of bad regions in a new graph and rearrange edges from the nodes of the previous graphs so that we obtain an admissible instance. Of course, this is not always possible, because maybe it's not possible to find an admissible instance from these cheating graphs. It is a requirement, so that the effort here is to finding a cheating graph where all of this is possible. And this is given almost for free in our case from a surprising work by Bogdanov in 2013 that is largely unknown. Basically, for each pair of C and chi, Bogdanov showed that there exists a graph that has chromatic number at least C+1, but locally is chi colorable within radius that is roughly our complexity. At the heart of this result lie topology and combinatorics, and the author also defines an operator between graphs, the join operator that resembles the join of topological spaces. And here, for the right graph family, we can keep the local colorability properties while increasing the global chromatic number. And just to give you the flavor of one of these constructions by Bogdanov, for the case C equals chi equals 2, so probably to get the lower bound of 2 coloring 2 chromatic graphs, this would be a cheating graph, so a 3 chromatic graph that has local chromatic number 2. I will not explain this. If anybody is interested, one can look at the original work by Bogdanov. Now we focus on the upper bound, which is based on the famous network decomposition algorithms. Well, an alpha D network decomposition is a technique that decomposes the graph in clusters, where each cluster has diameter d, actually weak diameter, which means diameter in the original graph, and clusters are colored with colors in this set, but adjacent clusters have different colors. And for example, this is a 3-6 network decomposition of a grid, so 6 is the diameter of each cluster, and we are using 3 colors to color the clusters. And it is not hard to see that if we are given such a decomposition, then we can find an alpha chi coloring in time roughly d. This is done by Barenboim in 2013. How? Basically, each cluster of color I will use a different a specific palette of colors which differs if the color of the cluster is different. And this is the palette, basically. And locally in each cluster we can brute force an optimal solution with chi colors, different colors from the palette, in time roughly d, because the diameter is d. So we'll get in total alpha chi colors. And for the case of the grid, we get 6 colorings, because 6 is 3 times 2. But we can actually do better, and the idea is what we call the hiding trick. Again, we suppose we are given an alpha d network decomposition, and the idea is to hide one color from the neighborhood of the cluster. This means that neighboring nodes of a cluster will not see a specific color. This is achievable by modifying a bit the clustering technique. I will not enter into details, but it is always possible to hide one color from the neighbors. And in this way, we can reuse this same color in all clusters, saving in total alpha minus 1 colors. So we get a coloring with alpha chi minus alpha minus 1, which is alpha chi minus 1 plus 1 total colors. And this is possible given a network decomposition, again in time, that is roughly the diameter of the clusters. This algorithm, given the network decomposition, requires only alpha in input, and alpha will be exactly our approximation ratio. So in the case of grids, if you use the hiding trick, of course the clusters will not look exactly like this, will be slightly modified, but we can obtain a 4 coloring where each cluster uses 2 colors, but basically the node that are on the border of each cluster will have always the same color. So you have to modify locally a bit the structure of the clusters. Now let's talk about the complexity of the upper bound in general for C-coloring chi-chromatic graphs. So what we do is we improve slightly the state-of-the-art clustering algorithms to get a network decomposition that works for alpha fixed and the diameter, where the diameter is roughly n to the power of 1 over alpha. In time, n to the power of 1 over alpha times some polylog. And given this decomposition, we know now that with the hiding trick and the technique by Barenboim, we can get an alpha chi minus 1 plus 1 coloring in roughly the same time. So the running time will not change, and if we fix alpha to be the approximation ratio, we know that the total number of colors that we are using is at most C, solving the problem. This matches the lower bound, and interestingly, the complexity of this problem increases with multiples of chi minus 1. So for many different values of C, the complexity will actually remain the same. And these are almost tight bounds that imply that there is no quantum advantage. So to summarize, before this problem was known in the classical local model only for the case chi equals C or chi equals 2 and C equals 3, only the lower bound part, but we solved the problem for any combination of chi and C. And we show the lower bound in the non-signaling local model, implying that there is no quantum advantage. And we also generalize the graph existential indistinguishability argument all the way up to the non-signaling local model for a more general class of problems, the locally checkable labeling problems, where coloring is just an example, but many other natural problems belong to this class, such as MIS or maximum matching, maximal matching, many others. So a natural question is, what else can we prove in this non-signaling local model? Both with this argument, but also what are other techniques to establish lower bounds in this model? This is unknown. For the upper bound, we show that this idea of the hiding trick is optimal, and we also give a slight improvement over existing network decomposition algorithms when alpha is fixed. Thank you very much, and I hope to see you at the conference.